So we have time for a more general discussion here now. We have heard 4 talks. First of, I don't know if Altschuler is still around. If you still want to ask him some questions about Andrei Sakharov. I cannot see Boris here, but Misha is here. So that would be an occasion, an opportunity to ask or take up some kind of discussion about that.
Yeah, if there are some questions, I can probably try to answer. But actually, I gave some comments in the morning. But the idea was just to give comments in the morning and in the evening because of the different times. So I can even repeat what I said in the morning for those who was not around. Very briefly, completing maybe what Boris said. And those who were at the opening, then they can relax for 3-5 minutes, let's say. I just wanted to mention the following. I mean, when Sakharov was exiled, he was still employed at Lebedev. And somehow it was organized so that scientists from our department were traveling to Gorky to somehow organize to have scientific contacts with Andrei Dmitrievich. And once, several times, I was there as well. And I just realized before this conference that actually I was talking with Sakharov on the issue that is very much in spirit of this conference, and namely on the higher spins. I can say that he was very much interested. He was trying to follow, but he was more interested in supersymmetry those days. That was early 80s, something like 81. But definitely he was interested in some fundamental questions in physics. And definitely that was one of the very many different subjects he was looking at. As an anecdote, I can tell you that, I mean, it was not very recently, it was like 40 years ago. And the life, especially in Russia, was organized, in scientific Russia, was organized very differently from how it is organized now. Now we are talking freely over Zoom or Skype or whatever, exchange information and take information from web. Those days, actually, the way of communication with how we were learning about new recent papers was just by receiving preprints. And believe it or not, Lars remembered this, of course, but I mean, others probably I realized recently that students of mine even don't realize how it was those days. So it took about 2 months for a preprint to reach from Europe to Moscow. So when we were getting them, probably not all of them. So when we were working something like 2 months behind, that we understood that we should really be very, very, very doing fast. So the reason why I'm telling you about this is that when we came to Sakharov, he was receiving a lot of mails, and in particular, he was receiving a lot of preprints from all over the board, and people were sending preprints to him. So he had some huge bunches of preprint, and to my great surprise, the time shift was much slower. So they were reaching Andrei Dmitrievich much faster than they were reaching us. So when visiting Sakharov there in Gorky, I took a bunch of preprints back to Moscow, from him that he was not interested in. And that was the way how new information came through, exiled person in Russia. So that was indeed very different story and very different time those days. I mentioned in the morning that Sakharov actually had very, very broad scope of interests. And maybe some of the other, I have been there 3 times, he said that he, if he would have a little bit more time and I don't know, maybe be a little bit younger, he would learn biology and would study biology. And indeed, he had a huge textbook in biology, actually, looking at. So that was indeed very great scientist, and in many respects, absolutely unusual. So somehow he was able to, he had very amazing intuition. And some people who were working with him on the bomb project, like, it was organized there more or less like a CERN now. And there were some competing groups that were solving the same problem. And for instance, Zeldovich, one of he was heading another group. And Zeldovich, was used to say that the way how Sakharov thinks is not at all clear, because he somehow were able to come out with the final result. And okay, it's not what it not only was the let's say qualitative conclusion, it was quantitative conclusion. So he was giving right numbers without computing. So that was indeed I mean, the only example in science that comes to my mind of that type is this Indian mathematician Ramanujan. I mean, it's not clear how he was thinking, but he was thinking right. Sakharov was something like that. That was kind of the same story. And actually, a lot of very interesting stories are about this military project, how it was developed, that we don't quite know very well. But he was really a great person and contributing also to fundamental physics, as Boris mentioned in his talk, and also I mentioned in the morning. So my conclusion was in the morning that having this session dedicated to Sakharov is not that strange, because actually he was interested in the whole physics. So this is an important part of physics, and I hope that we will make some progress with this workshop. I think this is all I can say now. So we can try to get together the speakers, if I don't know who is around at the moment, to start the discussion session.
Okay. Yeah, there's so much that could be said about Sakharov, of course. So it's, but we should go on. I see that the other speakers are here. So let's now start. Wants to be the first person to ask questions or comments to the 3 other speakers.
Can I ask some more question to Igor Klebanov? So I haven't quite understood, how could you derive some conclusions about the behavior of the potential in more details, maybe, from the analysis of the states, of the bound states of these gluing balls and things like that. So what is your logic? How you conclude that there is no confinement from the spectrum of these highly excited states?
Okay, yeah, I was very brief for that part. Maybe let me first say a couple of things about just the closed string sector, which was in some sense known for a while. But can I share the screen? Yeah, So basically the story is the following, that so if you look at, for example, bosons, we notice that some states in this boson sector look like composite states of two fermions. Yeah, maybe I'll.
Composite states of two fermion states.
They have masses, which their masses are sums of. So let's look at the lightest bound state, which is fermion, and its mass is 5.7. Mass squared is 5.72. Okay, extrapolated mass to large K. Then we noticed already in '97 that there is a continuum of states appearing at the mass squared, which is 4 times that, exactly 4 times that, which means that there are masses which are, the continuum starts with twice the mass of this lightest state. And this happens both in the fermion and in the boson sector.
Okay, and why does it mean that there is no confinement?
That means that it just falls apart. It's like just an observation that the state that should not be falling apart can fall apart into 2 states, which are these lightest states.
Okay.
Okay, and you see these states accumulating here. But moreover, there is at finite K, there is this exact degeneracy for this fall apart mode. And I just want to explain why this is. So we looked much more carefully, and all these orange dots are have these exact degeneracies. You again see this continuum starting here at 4 times the mass squared of the lightest fermionic bound state and so on. And I just want to say very quickly why this happens. So if you look at these organizing states into Kac-Moody modules, so for the states that are degenerate are these n equal 2 modules, which have 2 B daggers, and they turn out to be composites of this n equal 1 module with a single B dagger. This is just, you can check numerically, but we also have some calculation that shows why this happens.
So basically, you observe that some excited states, excited states, are split into 2 fermion states.
Yeah, into
That's
2 lightest.
That's why you conclude that probably there is no confinement. That's your logic, right?
And not yet. This we knew already long ago, okay? That there is this degeneracy, so it hints that, so basically there is some part of the spectrum that's really continuous. If these bound states would normally should be discrete, but here there is really a threshold and there is continuous spectrum starting from there. The schematic picture of how this fall apart happens is that the single string kind of falls apart into 2 strings. But let me just say what the new part that we did is that we looked at the same model coupled to a massive fundamental quark. Then there are these states like this with a massive quark, a massive antiquark, and massless stuff between them, right? These are the generalized mesons, so to speak. Then we look at the spectrum of these generalized massive mesons, and we again see that there is a continuum beginning at some value. And again, so now this, when you take massive meson state, there is nothing massless, so these are the lightest states. They can also fall apart into 2 mesons, which are massive quark with some massless screening cloud and massive antiquark with this massless screening cloud. And again, we basically observe the continuum appearing here. Am I making sense?
Okay, yes, okay.
It's just a very engineering approach. We just look at physical bound states. Normally, in a confining two-dimensional theory, you would just say the spectrum of physical bound states should be discrete through and through. The gaps can be small, but here we really see the exact continuum appearing above a certain threshold, and we interpret this as due to the screening.
Okay.
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 But then, so this is in the fermionic sector. But then, why do we say that there is something? If you look at the bosonic sector, again, we see the same continuum appearing, but then there is a bound state below this threshold at 6.55. And that we interpret, so conceptually, this is due to the fact that the potential is not exactly zero. It starts out being non-zero, but then it levels off. And then there will be, in the Hopf model, it just keeps going, right? It's just an exact linear potential. And we have a series of bound states here. But in this model, there is maybe one bound state, and then above this threshold, you see the continuum. That's basically the interpretation.
Okay, thank you.
I think what is definitely interesting is that even in the regulated theory with this finite P plus, a discretized P plus, we already see some exact degeneracy. I mean, you can try to read why this happens. But if you just forget about all those details and just look at what we think the extrapolated spectrum is, it really has a continuous part, and then there is a discrete state below it. That's basically.
Okay, thank you.
So it's a very pedestrian approach, just compute numerically the bound state spectrum. It's not fancy like a Margotsky approach, but we don't have access to his non-trivial vector here.
Personally, I just couldn't understand Komargotsky paper. Well, it's my problem.
But this, I think, if you can just, we did honest numerical calculations with millions of states.
Okay.
We really have very suggestive structure. I'm not sure I would call it a complete proof, but that's what it looks like.
Okay.
Okay. Isha.
Well, I have very pedestrian question. And I had very hectic time, so I'm even skipped part of your talk. But let me try. So this degeneracy. This is again about degeneracy. Mm-hmm. So can you somehow identify some operators that commute with Hamiltonian, and are responsible for this degeneracy? Maybe in this Kac-Moody language or whatever.
Yeah, that's one approach we had in the paper. We actually did find some supergroup operators, OSP14 operators that indeed commute with P minus.
Yeah.
But there is a slide called Hamiltonian P minus, and so some of it we could identify with some operators that commute with P minus.
And do they reproduce the whole spectrum in this? I mean, the whole degeneracy?
So these operators were applicable to, like when the quarks are massless, also we observe exactly equal P minus for different P plus. And this explained that part of the story.
Okay.
But the more general degeneracies, we can sort of argue for them using this Kac-Moody algebra.
And what are C and B in this formula? They should be made from the fundamental fields, from fermions, from gauge fields. The C and B.
Yeah, you mean P plus and P minus?
No. Q, that's the generator, right?
Right.
That's the operator which forms.
Yeah, they're written here. These are the formula for the Q.
Yes. And what are the notation? The C and B.
These are just the modes of the of the quarks. C with one index, they're the mode of the fundamental fermions, and B's are the modes of the adjoint fermions.
So it's made out of quark and
yeah, it's basically an operator which is like psi bar, like a cubic operator, which is gauge invariant.
Okay, but
Yeah,
this commutator, you in this particular paper, you shown that they commute with this p minus in the infinite n limit, right?
Yeah, in the infinite n, yeah, these ones were for infinite n.
Okay, okay.
I mean, there are a couple different approaches. One was this approach with this OSP supergroup, but the other one is this older approach of Kutasev and Schwimmer through this cut-smoothie, basically current algebra.
Okay.
Yeah, so we basically understand where the degeneracy come from at finite k. I think you can essentially turn it into a proof of continuous spectrum.
Excuse me, may I ask a little bit more on this issue?
Please do.
So if you have this OSP14, so basically what you consider, I guess, are some unitary representations of OSP14, right? Is that correct?
Yeah.
Well, they are very well known. They are infinite dimensional, so that is a very delicate test. I mean, to arrange the states in terms of unitary representation of OSP14. So you say that this is precisely fits like that.
Right. I mean, the one subtle thing is that these q plus minus, little q plus minus, they shift p plus by 1 unit. That's basically this equation.
Okay, yeah.
So you have to look at the set of states for all values of k. Kind of k is the number of units of p plus.
Okay, let me just make, I mean, naive comments or question. Well, this is about, again, ADS-CFT, in a sense that this is about the representations of OSP14. It's Flatter-Fronsdal theorem, basically, and its extensions. So that the towers of states that appear should be related to singletons, to massless, to currents. To...
Yeah, we did notice this. Yeah,
okay.
I mean, we don't know the precise physical connection, but somehow, yeah, in this, yeah, it's basically one thing we did is we looked at the spectrum of these mesons in the massless case, and we observed these exact straight lines.
Yeah.
Basically, changing p plus does not change p minus, and then we found this explanation. Yeah,
okay.
Again, I don't know if we have the fully elaborated story, but I think this is the explanation.
Okay, thanks.
If it's OSP, then there should be some supersymmetry, but there is no supersymmetry.
There is no physical supersymmetry because this actually shifts p plus while preserving p minus. So the mass squared does change under this. It's kind of a symmetry in this light cone gauge. Yeah, but you see that due to this degeneracy that you see at finite k, you have a whole bunch of mass squareds converging to the same value. So this picture shows that in the continuum limit, you really have this continuous spectrum starting from this 572, which is sort of another way to say that there is some non-confinement going on.
Okay. Do I see any more hands here?
So I'll stop sharing then. Thank you for the interesting questions. Yeah, I mean, you can look at the paper.
I looked, but it's better to ask the questions and get the answers.
Okay, let's see. For the other two talks, they were a bit interrelated, so we might have more or less common questions to the two speakers, or they are whatever, but now we have the chance of asking questions to the speakers. Because U-duality and T-duality are very important concepts in modern theory. They're really remarkable concepts.
Yeah, may I ask a question to Ilya, please?
Yes, Igor.
Yes, thank you. Ilya, you have said that you have some intrinsically non-geometric or intrinsically double field theory solutions. But then you commented that these solutions satisfy section condition. How it could be? Because if they are essentially double field theory, this implies that they depend on both coordinates. So you mean that there are some solutions of section condition which does not eliminate dependence on one of the coordinates?
Yeah, that's right. They do eliminate half of the coordinates, but they keep a pair which are dual to each other.
Mm-hmm.
So you have a pair of two dual coordinates. You have to eliminate half of them, right? Essentially, half of 20, let's say. So you eliminate them in such a way that you keep x and x tilde, which map to each other under T-duality, and then this is non-geometric.
But then you change the coordinate basis and you have geometric.
Yeah, you can say that probably. Well, from the point of view of the original basis, this will still be non-geometric because this is a sum.
No, from the point of view of basis, I agree.
Yeah, I also agree with what you said. Yeah, you can do that, such a change.
Yeah.
That's right.
Okay, thank you.
Thanks for the question.
I had a question. I'm sorry, I will not be probably able to even properly ask this question, but let me try also to Ilya.
Yeah.
Can you show your slides? Is it difficult to?
Yeah, sure, I can. 1 second. Here you go. Can you see them?
Yes. So when you impose your conditions on the supersymmetry parameters, how was it called? Well, the crucial conditions that allows you to go for Busher rules, right?
Mm-hmm. Yeah, maybe.
Where is it? Yeah.
Maybe this, maybe that. The abelian constraint.
Yeah, this abelian constraint, right? Mm-hmm. So I would like to understand better the status of this statement. I mean, what I understand is that if this is true, then you can proceed. What I don't quite understand, if it is not true, does this mean that there is no way, or it means that you just don't know how to proceed?
I think it means we did not know until now. Yeah. So
until the yeah.
What I proposed is the way to do that.
Yeah.
So it wasn't known essentially. The original papers, if you just look at Berkowitz, Maldacena paper, for instance, they just say that this is the Busher procedure and a separate phrase saying that it must be abelian, because otherwise it doesn't work. It's true if you use a killing spinner which is non-abelian, then you get something which is not a solution and it's easy to check. But then the question is how to do it when it is non-abelian, because you like to be able to do that. And then this is the suggestion how to, of one of the possible ways.
Yeah, this is one option that you suggest, as far as I understand, right?
Yes, that's right.
Okay, so let me just looking at this formula 10. Basically, as usual in supersymmetry, when you consider some anticommutator of super transformations, you will get some kind of translations or something. And this is the origin of the, I mean, that is what you want to compensate by choosing two parameters to satisfy this abelian condition, right?
Yeah.
So if you relax, you go to, non-abelian case or whatever, how do you call it? So this is very much similar, and in fact, very deeply related to going from Minkowski to anti-de Sitter, for instance. And Minkowski translations do commute, and anti-de Sitter they don't. And it's very much similar story. So can you do the same with the usual geometric stuff by going to a curved space, by introducing some kind of non-abelian, I don't know what, scheme that would work in that case as well?
Do you mean?
Maybe it's not specifically relevant to your problem, to string theory, and but in general, as a matter.
I'm not sure I understood you right. So you're saying you're talking about bosonic T-duality in standard space without fermions? Or,
Yeah.
Yes.
Yeah.
Right. I don't know. I don't see the direct analogy. So the way T-duality is defined in non-abelian case for bosonic translations, well.
Yeah, I'm sure that this is not directly extendable to that case. What I'm trying to say, but basically, you introduce some, you consider some symmetries which are roughly abelian, and that is the starting point for in the standard case. Right?
So here the crucial point was that the two supersymmetries anti-commute or commute, if you like, for a bosonic shift.
Yes.
So for two bosonic shifts, you will get another bosonic shift.
You will get rotation.
Yeah, right. So, right. So maybe it is possible to describe it that way. I don't know of that. So that would be then T-duality with respect, or kind of a double field theory setup where this extra T-duality is with respect to this rotation then.
Yeah.
But this is just pure speculation. I don't know.
Yeah, I understand. But I mean, this is more or less how the question is settled. So it's speculative. Okay, thank you.
If I'm not mistaken, Eric Plauschen had
spherical T-duality. Yeah, I remember.
Yeah, some papers on T-dualization along rotational
spherical T-duality, but I don't know.
Okay, so thank you.
Okay, there is a Tima Sorokin.
Yeah, thank you. Maybe just first a small comment about the question of Misha. I think your question is basically have roots in the non-abelian bosonic T-duality, which people studied quite intensively, I would say. So, and some of the examples which people studied, they correspond to what you asked, Ilya. I mean, basically, if you take a symmetric space, then this symmetric space has commutation relations similar to what to the
this is exactly the point.
Yeah. So yeah, the answer is basically yes. So then the question is, can you reformulate these things in terms of double field theory? Then this is the question to Ilya and his collaborators, of course. But my question is actually about the bosonic isometries on which your fermionic isometries close. Do you have examples when these bosonic isometries don't commute, or are they commuting isometries, or not always? So that's related also to the bosonic non-abelian T-duality.
I think we didn't go that far yet. So we mostly concentrated on the easiest case where you have just one supersymmetry, and correspondingly there is just one bosonic supersymmetric killing vector which you built out of that. And these together are like a sub-algebra. But we do have a couple of examples where we have several killing spinors and correspondingly several killing vectors as well, but those are all very simple and they are commuting. It's like just shift in two different directions. I think you can probably build up something more complicated. It would be then a mixed, you can say, T-duality where there are some fermions, some bosons, and then you T-dualize.
Yeah. And then it goes again in the direction of the question of Misha, basically.
I would think that in general, if you end up with some algebra of killing vectors which don't commute, you should expect further non-abelian bosonic T-duality along these directions.
Right. Yes, of course.
But it's I don't really understand how to do that for general backgrounds. I mean, for group manifolds, it's sort of more or less just ideologically clear, but for general backgrounds, I mean, we can do fermionic for general backgrounds, but further bosonic is subtle.
Okay, thank you.
So Ivanov.
Okay, Ilya, can you show the first transparency where you started to discuss fermionic duality? Yes.
1 second.
Yeah.
Maybe this one.
Earlier. Where you consider transformation of theta 1, yes.
The shift.
Fermionic, yeah, this one. I don't understand quite well why you consider only a shift of fermionic coordinate, but x also transform under supersymmetry through theta and epsilon 1.
Yeah, that's right.
Bosonic coordinate also is transformed under supersymmetry.
That's right. Probably that's the reason why they wanted to consider abelian. In the abelian case, they wanted to consider. They wanted to start with the abelian case. So essentially, that was the requirement that this shift.
Okay, so it is not genuine supersymmetry, but some kind of
a very special
truncation or something.
Yeah. So yeah, it's a shift of a fermion, but it does not generate the shift of x somehow.
But if you consider also transformation of x as a normal superspace approach, then what kind of complications you get in this case?
I don't really remember, but I think this should be done in its own right. This hasn't been done, to the best of my knowledge.
But you you stated that this is superspace. But in normal superspace, supersymmetry also transforms bosonic coordinates, not only shift of fermionic coordinates, but also x is transformed through theta. So it is not a standard superspace, it's some kind of, I don't know. Of course, any extension of x by fermionic coordinates, you can
this maybe this is just because in the end we are interested in the theta equals 0 components of all the fields, because we are I only care about supergravity.
So purely bosonic part of
yeah. So I go to the lowest order in theta, term the expansion of all the superfields, and then I get my superstring background fields, right?
So you put theta equals to 0, actually.
Yeah. I should have.
I see. Okay.
Clear.
Maybe if I can I comment on this?
Sure.
Yes. So I think here it's more because. For example, in 10 dimensions, the supersymmetry algebra is very large, and some of the generators anti-commute if we only require if we consider some sub-algebra of the complete supersymmetry algebra. So there are some generators under which bosonic coordinates don't transform. I mean, some supersymmetry generators which not transform under supersymmetry in 10 dimensions. And then you use them to perform this fermionic duality.
Okay, thanks.
So, do I see any more hands up? Well, I said 2 hands, but I don't know if you're still interested in asking questions. Misha, are you?
No, Lars, thanks. I just forgot to remove it, I guess. No.
If not, I think we should close the session. I think it's perfect on time, which I guess is non-standard. It used to be non-standard in Moscow in the old times when talks and seminars could go on forever. And but this is a new format, new generations. People are more polite, perhaps, or also eager to dwell into long discussion. It's difficult to do, perhaps, on this forum. So then I would thank the speakers, and so looking forward to the rest of the meeting. So, okay.
Okay, thank you very much. And it's thanks to the chairman, actually,
Thank you.
to be on time. Yeah. Okay, very good. Okay, see you tomorrow. Bye-bye.
Thank you. Goodbye.